Okay, so moving on to the actual test. What we're going to do now is we're going to do a significance test to see the difference between RHS and Mount Whitney students' Facebook habits. So as you can see, we've got our two-way table back again. So I'm going to go ahead and fill in the totals from the other side. We had 20 students total that have not much Facebook habits, 30 that says one or more per week, 50 that says one or more per day, and that's between both schools. So that's a total of 100 students that I surveyed. But at RHS, there were 50 students I surveyed. At Mount Whitney, there were 50 students I surveyed. Okay, so we've got those totals back in, and we need those because we have to use those to find the expected counts. And that's what it's asking us to do here, complete all of the expected counts. Okay, so if you remember from the last video, in order to find the expected counts for not much RHS, all you got to do is take the row total times the column total, divide by the grand total. So in this situation, it's 20 times 50 divided by 100. So that gives you a expected count of 10. This one, again, row total times column total divided by grand total. So that would be 30 times 50 divided by 100. That gives me an expected count of 15. And last but not least, 50 times 50 divided by 100. That's how you would do the expected count. We would get 25. Okay? And so I like to put my expected counts in parentheses just to show that that is an expected count. And actually, every single one of these is going to have the exact same expected count. If you don't believe me, you can go and try it. But if you think about it, both of these have a row of 20. Both of these have a column of 50. So you're going to get the same exact expected counts. Okay? So we found our expected counts. And really, that's one of the biggest difference between a goodness of fit test and a test of homogeneity. When we get to actually calculating the chi-squared, it's exactly the same. All right. So let's go ahead and use these totals now to answer the next question. Does the data provide statistically significant evidence that the students at RHS have different Facebook habits than the students at Mount Whitney? So again, we are hoping to see that Redwood's different than Mount Whitney, because of course, I mean, we're Redwood, we're better, right? So we want to see if they're different. That's what we're hoping to show. That would be our alternative. So if we're hoping to show that Redwood and Mount Whitney are different, then what are we supposed to assume? Hopefully you're thinking we have to assume that we're the same. So here's the state portion. For the null hypothesis, there is no difference in the distribution of Facebook habits between Redwood students and Mount Whitney students. We're assuming that we're the same, okay? Now again, we're hoping to show that we're different. So our alternative is just that there is some difference in the distribution of Facebook habits between RHS and Mount Whitney students. I don't know why that's coming out kind of blurry, but I just put in the word some. We don't have to show that there's a great deal of difference. We're just trying to show that we are different. Now in all states, we got to state our alpha. So let's go ahead and use an alpha of 0.05. Okay. Now, in the plan, again, we have to name it. We're not going to say chi-squared goodness of fit anymore. It's chi-squared test of homogeneity. You got to make sure that you're giving the appropriate names here. Okay. So, chi-squared test of homogeneity. All right. So, like all other plans, we got to do our conditions. The random condition. Now, because we're testing two samples, notice that I'm referring to both samples. Both samples were random. And then I quoted why. Random sample from each high school. Think of this as the tests that we did with two samples. When we did the plan step, we had to talk about both samples. We had to say it was random for the first sample, it's random for the second sample. You have to do the same thing with test of homogeneity because we took two separate samples, a sample at Redwood and a sample at Mount Whitney. So we have to say that they were two separate random samples. Okay? Same thing with the 10% condition. Notice I said it twice. 50 is less than 10% of the Redwood population. Remember, we're about 2,300 students at our school. 50 is less than 10% of the Mount Whitney population, because remember, they have about 1,800 students at their school. That's rough estimates, but I think we're pretty safe. And notice that I said it's a 10% condition, again, for both samples. I have to refer to both. Okay? And then for the large sample size condition, again, we're not checking a normal condition because we're not using a normal curve. We just do the large sample size. All expected counts are greater than or equal to 5. And again, I can go ahead and say C above. Because, remember, we did all the expected counts above. All of these are my expected counts. So you may want to come in here and point to it and say these are the expected counts. It shows the reader that you did indeed check the expected counts. You can't just assume that the expected counts are greater than or equal to 5. You have to show that you checked them. So if you do that and you label it up there, it's fine just saying C above. All right? So there's our plan step. That's pretty much the only differences between chi-squared test of homogeneity and a chi-squared goodness of fit. The rest of it is the same. In the do portion, we're going to draw the picture. Remember, it's a skewed to the right distribution. Not my prettiest curve, but chi-squared. Again, make sure you list the degrees of freedom. So it's a chi-squared test with the degrees of freedom of, I don't know if you remember how we did this on the last video, but if I look above, I could technically use the formula R minus 1 times C minus 1, which is rows minus 1 times columns minus 1. But if you remember, what you can do is think of it as you chopped off a column and you chopped off a row. I'm not going to do the totals. I'm doing the actual numbers in the boxes. And if you can see, we've got 1, 2 numbers left. That ends up being the degrees of freedom. Okay? So the degrees of freedom is 2. So we got to find the chi-squared value. Okay, once we find the chi-squared value, we can plug it into our calculator and figure out what's the p-value. So chi-squared is equal to the same formula we used the other day. I got to say the sum. We're going to find the sum of all the observed minus expected squared divided by expected. Okay, now this is where your calculator comes in super handy. I'm going to go ahead and switch to the calculator view because remember, there's a whole bunch that we have to do here. So what I would do is put it into your lists again. List 1, I'm going to list all of the Redwood students first. 14, 11, 25, and then Mount Whitney students. 6, 19, 25. Now, this is all of the expected count, or I'm sorry, the observed counts. Okay, I listed the 3 Redwoods and then the 3 Mount Whitneys. You just kind of have to pay attention to which one's which. List 2 is the expected. So 10, 15, 25, 10, 15, 25. Because remember, these have to be linked together. Expected, or observed, expected, observed, expected, observed, expected. These 3 are the Redwood. Observed, expected, observed, expected, observed, expected. These 3 are for Mount Whitney. Now, because I'm going to do the formula on all 6 of these, I'm just going to have my calculator do it once. List 1 minus list 2, observed minus expected, squared, divided by expected. So if you tell it to do all of those lists, when you hit enter, they all pop up right away. You don't have to do it 6 different times. Okay, so feel free to write those down. I will write them down on my paper as well. First, I got to show the work, though. I want to show the reader that I know what I'm doing. So I'm going to say 14 minus 10 squared divided by 10. That's observed minus expected squared divided by expected, plus 11 minus 15 squared over 15. Now, to save us some time, I'm okay if you go plus dot dot dot. Those are the first 2 for Redwood, so I'm going to say plus. Now I'm just going to show the last one for Mount Whitney. 25 minus 25 squared divided by 25. because I'm not actually having to do all these out, I'm fine if you show a little bit of the work to show that you know the process of the formula, and then you can go ahead and write those values out. We know that it's 1.6 plus 1.1 plus 0 plus 1.6 plus 1.1 plus 0. Okay? So, chi-squared equals the sum of all those. If you add all those up, you get 5.33. There we go. So there's our chi-squared value. That's what we're looking for now. What is the probability of obtaining a chi-squared value of 5.33 or higher? Well, just like we did yesterday, we're going to do chi-squared CDF. We're going to give the lower bound, which is the 5.33. If you look at the picture, that's the lowest bound. The upper bound is something quite large, 999, with the degrees of freedom of 2. Okay, so just to remind you guys how we do that, it's a new distribution, so we're going to go second distribution. We're going to the distribution portion of the calculator. It's right here above bars. Okay, you can see option 7 is chi-squared PDF, but we want chi-squared CDF. So if you scroll all the way down, it's option 8. Okay, so, oh, I was in the wrong window here. Let me try this again. Chi-squared CDF. So the new calculators, this is my old stuff from the last time I ran it. I'm going to say 5.33 is my lower bound. My upper bound is 999. This time I have a degrees of freedom of 2. The older calculators, you type it in with parentheses. Okay? And again, once you hit paste on here, it pops up with the exact same thing. So there is our p-value, which it is small, but is it small enough? Not according to our alpha, so that's interesting. So let's come back to this page. Again, you want to label that. This is our lower bound. This is our upper bound. This is our degrees of freedom. It's important to show the reader that you know what those pieces are. We got a p-value of 0.069, or basically 0.7. Okay? But we've got our two most important parts. We've got our chi-squared value. We've got our p-value. That's what we need for the do portion. All right, last but not least, the conclusion. Assuming the null hypothesis is true, there is no difference in Facebook habits between Redwood and Mount Whitney students. There is a 0.069 probability of obtaining a chi-squared value of 5.33 or greater, purely by chance. What type of evidence does this provide? Weak. Remember, this is not smaller than my alpha level of 0.05. Therefore, it's weak evidence against the null hypothesis and is not statistically significant at alpha equals 0.05. And why? That's because 0.069 is greater than 0.05. Okay? Therefore, we fail to reject the null hypothesis and cannot conclude there is some difference between Facebook habits of students at Redwood and Mount Whitney. Now, notice I don't have my follow-up here. I don't need the follow-up. I didn't reject the null hypothesis. In other words, I don't have enough evidence to show that Redwood and Mount Whitney are different. There's some evidence, there's definitely some, but there's not enough evidence to go ahead and conclude that we're different. So we failed to reject the null, your conclusion stays the same. You don't need the follow-up. Okay, so there's our, actually we've got just a little bit more on this page. Last but not least, just showing you guys the difference between goodness of fit and test of homogeneity. As you can see, there's slight differences in the test, like expected count. But how do you know the difference? Well, a goodness of fit looks at one variable in one population. If you think about it, we looked at one variable with Skittles, color, and we only looked at one population, all Skittles. In this case, we still looked at one variable, Facebook habits, and how many populations? Well, in this case, it was two different populations, Redwood and Mount Whitney. So that's the difference between a goodness of fit and a test of homogeneity. So I'm going to go ahead and end this video. You can watch the third video for the third example, but go ahead and give it a shot before going through my video. Okay.